Hello guys, welcome back to my channel Maths for All by Saurabh. So in last chapter we have learned arithmetic progression and we have solved some practice set questions. Okay, so if you still have any doubt, then please comment on that video, so I will be looking those issues and will reply on that. Okay, and now today we will be covering the chapter 6 triangles. Okay, so we will cover what are the similar, this is the agenda. So we will cover what is the similarity between two triangles, congruency, what are the real world problems, how it will solve the real world problems. Okay, Thale's theorem and some other theorems that we need to prove, and some examples, and some of the similarity condition like AAA, SAS and SSS, and some examples. Okay, so we will be covering all these points in the chapter 6 triangle. Okay guys, now let's understand what is the similarity. Similarity between two figures when they have the same shape but not necessarily the same size. Okay, so but in the congruency we learned in our in a previous class 9 that the congruency when they both have the same shape and size. Okay, but in the similarity there is no requirement of the same size. Okay, the only thing that the ratio of the size should be in proportional. Okay, so what is the condition here? Same shape and corresponding sides should be proportional. Okay, so this is the condition for the similarity. For example, this circle, okay, and this circle, okay, and or for example the same radius. Okay, this is r, or this is something 2r. Okay, now you can see these two are congruent and these two are similar. Okay, because they're same, they have the same shape. Okay, and size is also same, but here you can say this they are not same size. The shape is same but they are not same size, so that's they are similar triangles. Okay, similar circles. Okay, let's suppose this one, okay, and let's suppose this one. Okay, now all these are these two figures are equilateral triangle, let's suppose. Okay, now you can see all angles are same, all sides means are proportional. Okay, so they are similar, they don't have the same size, so hence they are not congruent. Okay, in congruency we also need to prove that they both the shape have the same size. Okay, so these are congruent. Okay, and these are similar. Okay, now let's come to the real world problem. For example, the height, for example, this is our Mount Everest. Okay, okay, for example, this is our Mount Everest. How you guys understand how the actual height of this Mount Everest calculated? Do we need to go with the measuring tape to measure the height of the Mount Everest? No. Okay, how we measure the, for example, this is moon and this is our earth, right? How we check the distance between earth and moon? Okay, so we never use the measuring tape, right, for this distance. So we use the property of the similarity. Okay, for example, this triangles. Okay, this triangle, something height, okay, one side. So this proportionality, similarity we use to calculate the height of the Mount Everest or distance between Earth and Moon or any long distance. Okay guys, now come to our next topic, equiangular triangles. These are those triangles whose angles are same. Okay, for example, I have one figure, this one triangle. So this angle is 30 degree, this is, let's suppose, 90 degree, and this is 60 degree. Okay, now we have one more figure. This angle is 90 degree, this angle is 30 degree, and these are 60 degree. Okay, so the angles are same in both the triangles, so these triangles are equiangular triangles. Okay, now there's one important concept here. If any two triangles are equiangular, means they have the same angle, then their sides are also proportional. For example, this is triangle ABC and this is triangle DEF. Okay, now you see, right, angle A is equal to angle D. Okay, angle B is equal to angle E, and angle C is equal to angle F. Okay, now this triangle ABC are similar to triangle DEF, as we know, right, from the similarity theorem. Okay, now the ratio of their side is also same. Okay, see AB this upon DE is equal to BC upon EF is equal to AC upon DF. Okay, so this is C. Okay, so this is the basic theorem of proportionality, and this is also called the Thale's theorem. Okay, so Thale's theorem says that if two triangles are equiangular, means their angles are same, okay, then the sides is also proportional. Okay, so this is the Thale's theorem. Okay, this is a basic theorem of proportionality of the triangle. Okay, now let's come with more example. For example, you have drawn this line. Okay, so this is A and this is X and this is Y. Okay, now draw some points, right, like B, C, equidistance point, you can say C, D, E. Okay, now draw a line like this which cut here at B dash. Okay, now draw a line parallel to this one, okay, and it cut at C dash, and parallel line to this which is cut here AY at D dash, and some parallel line with E dash which is parallel to DD dash. Okay, now you can see this angle is same. Okay, and if these lines are parallel, so angle will also be same, right? For example, this is X angle, so this is also X, so this is also X, so this angle will be same. Now if this angle is common, right, if in all this triangle, so this angle should also be same. Let's suppose this is Y. Okay, this is okay. Now any triangle, for example, if you take this triangle ABB dash has same angle like ACCC dash. Okay, now all these triangle have the same angles. Okay, now this side is also proportional. Okay, now you can see, for example, this is 1 unit length, right? This difference is 1. So AB is 1 and AB upon AC, right? This is the proportional. So if it will be 1 by 2, right? 1 by 2. Now if you measure this length, right, this length or this length, this will also be same like this one. Okay, it is 1. Okay, so for example, this AB dash upon EC dash, so this ratio, right, will also be same. Okay, which is 1 by 2. Okay guys, now let's prove one theorem. Okay, so this theorem said that if any triangle ABC, if we draw a line parallel to the base, right, here this BC, then it divides the other two lines in the same ratio. Okay, so this AE upon EB will be AF upon FC according to this theorem. Let's prove this theorem first. Okay, now let's join this one. This line are parallel. Okay, so we have given EF parallel to BC. Okay, now draw this perpendicular to this one. Let's suppose this is N and perpendicular on this one which is M. Okay, now see the area of triangle, this one AEM. Okay, AEF. Okay, area of AEF, देखिए AEF. So base is AE, half of base which is AE into height. Height is NF. Okay, now area of this one EFB is equal to half of base. If you see for this one, right, BEF, so we will be see base is BE and height is same NF. Okay, okay, now take area of this one EFC. This will be half of base. Base is EFC, right? So base is FC and height will be this perpendicular EM. Okay, okay, and also for this triangle EFB we can also take area like EFB, EFA for this triangle, right, EFA, the base is, let's suppose, AF and height is EM. Okay, now divide equation 1 and 2. Okay, you will get AEF upon EFB, area of AEF upon EFB is equal to, if you see this half cancel, NF will cancel, this AE upon BE. Okay, okay, and for equation 3 divide by equation 4. Okay, divide this one, you will get area of EFC upon area of EFA is equal to half cancel, EM cancel, it will be FC upon AF. Okay, now you guys see area of AEF, this one, right, is common here, AEF. Okay, this is same. Okay, now EFP. Okay, now guys, one important thing, area of this triangle BEF and EFC is equal, and area of BEF is equal to area of EFC. Why? You know, right, these two lines are parallel. If any triangles are drawn between these two parallel lines, will have the same area. Okay, for example, these are two parallel lines. Okay, and you take 2 points here, AB, and if you take any triangle, okay, any triangle, if you drawn with from this 2 points which intersect one point at here, it will have the same area. So these two lines are parallel, so if I draw this triangle or this triangle, they will have the same area. Okay, so now you can see this AEF, EFA, this is same area, and then this BEF, BFE, right, this one and this EFC are same area, have same area, so this ratio will also be same. So AEF upon EFB, which is AE upon BE, is equal to this one, right, AEF is similar to EFA, AEF similar to AEF, this one, which is AF upon FC, so we will be say AF upon FC. Okay, now see what these lines are in this triangle. So this is AE upon BE, AE upon BE, and AF upon FC. So this is what we need to prove. Hence proved. Okay, so this theorem says, let me summarize this. So if there's a triangle and if we draw any line parallel to this BC, which is a base here, okay, then this line divide this other two sides in the same ratio. So BC, like EF is parallel to BC, and this intersect at E and F here. So AE upon AB is equal to AF upon FC. Or you can also say AE upon AB is equal to AF upon AC if you add +1 here in the both sides. So AE plus BE will be AB, and AF plus FC will be AC. Okay, so this what we need to prove here. Okay guys, now come to our next theorem. So in this theorem says, if in a triangle, if a line divides two lines in the same ratio, then line should be parallel to the other third line. Okay, for example, this figure. Okay, so for example, this triangle ABC, and if any line, for example DE, okay, if this line divides the opposite sides in the same ratio, then this line should be parallel to the third line. Okay, now we need to prove it. Let's prove. Okay, so as per this theorem, we know AD upon DB is equal to AE upon AC. So this theorem says that this line divides this lines in this ratio, in the same ratio. Okay, now we need to prove whether this line are parallel or not. Let's suppose these line are not parallel. Okay, so this one E dash. Okay, this DE dash is parallel to BC. Okay, let's suppose, assume DE is not parallel and DE dash is parallel. Okay, let's assume this one. Okay, Okay, now DE dash is parallel to BC. So as per our previous theorem, this line DE dash divides the line this in same ratio. So AD upon DB is equal to AE dash upon E dash C, right? So now we know AD upon D is AE upon EC. So it will be AE upon EC is equal to AE dash upon E dash C. Okay, so this AE upon EC is equal to AE dash upon EC, means they both are actually at the same point. So this implies that E and E dash are same point. Okay, now we can again prove more by adding 1 here. So add +1 both side. If you add +1 both side, right, it will be AE plus EC. AE plus EC upon EC is equal to AE dash plus E dash C upon E dash C. Okay, now AE plus EC, guys, AE plus EC is AC. So AC upon EC is equal to AE dash plus E dash C is AC upon E dash C. Okay, now AC is same, so we will cancel out. Now implies that EC is equal to E dash C. So EC will be E dash C. So both are same, which implies that E and E dash are same. Okay, so means our assumption that this line are not parallel and E dash line is parallel. Okay, so this is wrong. So because both points are same, so DE is parallel to BC. So this is what we need to prove in this theorem.